Hello, and welcome to the Excitable cells as dynamical systems, part 2, bifurcations in a simplified model of a neuron. My name is Alexey Braza and I'm from Moscow State University. In this lecture, we'll use a simplified conductance-based model to understand how a neuron can switch from quiescence to spiking and back from spiking to the resting state. So this is the model we shall use as our workhorse. We can believe it's kind of a faithful model of a neuron, but still very simple. As you can see, it employs the Hodgkin-Huxley formalism and describes two voltage-gated membrane currents. The first current is the instantaneous sodium current without inactivation. That's why it's called a persistent sodium current, and it's instantaneous, meaning that we don't regard the actual dynamics of the activation variable, activation gate. We just think it changes instantaneously. And the second current is the potassium current, voltage-gated potassium current of the delayed rectifier type. And it has a single activation gate, and we don't regard any cooperativeness in this gate. So hence the name of the model, persistent sodium plus potassium current model. And this model has only two differential equations, namely one for the membrane potential and the other one for the activation gate of the potassium current. Now, this greatly simplifies the analysis and allows to understand the dynamics of a neuron on a phase plane. So both potassium and sodium currents have their own voltage dependencies, and they are depicted in this figure. So this is for the sodium current, and this one is for the activation of the potassium current. So these are the steady state activation variables for each membrane voltage. The null lines for this model are easy to derive analytically, and they're shown in the bottom graph here. So these are the null lines. The red here is the null line of the membrane voltage, and the blue one is the null line of the activation gate of the potassium current. Note that any change in the amplitude of the applied current here, so this is the current we stimulate our neuron with, so any change in it will just shift the V null line upwards or downwards depending on the sign of the applied current. So depolarizing currents will shift the V null line up, and hyperpolarizing currents will shift the null line down. And well, this will define the change in behavior of our dynamical system, and the actual shape of the null lines will define what kind of bifurcations there will be occurring. Intersections of the null lines are, of course, fixed points or equilibria, just one here, for example. And they can be either stable or unstable depending on the corresponding eigenvalues. Just as a quick reminder, all phase trajectories will cross the V null lines vertically and will cross the N null lines horizontally. And of course, any point on the phase plane is the state of a dynamical system. I should note that this model is practically equivalent to the well-known Maurice-Licard model of the giant barnacle muscle fiber, except that there is a calcium current in the Maurice-Licard model and sodium current in this model. Though this model is kind of simple and doesn't have a lot of equations, but it still captures the main properties of neurons, main excitability properties of neurons. And we will discuss this right now. So, a change in number or stability of an equilibrium point leads to a change in system dynamics, and it's called a bifurcation. Let's look in more detail how a model neuron can switch from a resting state to periodic spiking. If we allow the change in only one parameter, for example the applied current, then the neuron can lose stability via one of the four scenarios depending on the values of other parameters, or the shape of the null lines, for example. First, as we shift the null line up, the two equilibrium points, the stable node and saddle, can merge together and annihilate, leading to a creation or a jump to a limit cycle. So these are the two bifurcations when the node and the saddle move towards each other as we shift the real null line up, annihilate, and therefore the system can't dwell here anymore. It will either jump to an existing limit cycle, or the limit cycle will be created presently. These two bifurcations are called saddle node bifurcations, and neurons near these bifurcations display certain neurocomputational properties which allow to call such neurons integrators. And when I say neurons near these bifurcations, what I actually mean is that the actual physical properties of real neuron can be described by a dynamical system where the parameters organized in such a way that the dynamical system is near the saddle node bifurcation. On the other hand, for example, when the potassium current activates at more hyperpolarized membrane voltage, so it's more sensitive potassium current, there is a single equilibrium point, namely a stable focus, so all trajectories will rotate around it and finally fall on it, so it's a stable focus. Then it loses stability and becomes as unstable as we shift the V-null line up or inject a depolarizing current in a neuron. Depending on the condition, if there is already a stable limit cycle attractor at this moment, or it is born simultaneously, the bifurcation is either subcritical or supercritical Andronov-Hopf bifurcation, respectively. Because the neurons near such a bifurcation have dumped subthreshold oscillations, these neurons can be called resonators. It is important to note that although we use the simplified model to demonstrate the bifurcations, any dynamical system can switch from resting to spiking state or oscillations via one of the four main bifurcations described here. And this is in the case that the bifurcations is codimension 1, that is, it is brought about by changing a single parameter. While arguably such a situation when a change is only required in a single parameter is more likely to happen in nature in real neurons than bifurcations requiring simultaneous change of two or more parameters in a coordinated manner. Now let's look in more detail at saddle node bifurcations. We have two cases here. In both cases, the node, stable node, and a saddle move towards each other and coalesce, resulting in a saddle node fixed point, which is a saddle on one side and it's unstable, and it is stable and a, so to speak, node on the other side. And that's why it's called a saddle node or fold bifurcation. So there are two scenarios. In one scenario, which is called a saddle node off invariant circle, there's a C here. Just a moment, I'll make it right. That's off invariant circle. And this is a bistable system, meaning that although a neuron can be in a resting state, quiet, not spiking, but this stable state has a limited attraction, basin of attraction. So if we suddenly stimulate a neuron with a short pulse and move its state horizontally along the v-axis, it will then find another stable attraction, which is here a limit cycle. So another stable attractor is a limit cycle, and it will be spiking. So depending on where we start, either we start near the node or either we start in the attraction, basis of the limit cycle, we will get either sustained spiking or resting for the same combination of parameters. And this coexistence of two different kinds of behavior is important for example, bursting of a neuron that is spiking in short or long batches of spikes interleaved with quiescent periods. In the other kind of the saddle node bifurcation, the limit cycle attractor is born simultaneously with the vanishing of the saddle node equilibrium. So this is saddle node on invariant circle. What happens here is at the moment of bifurcation, we have this saddle node equilibrium point, and any trajectory that will start from this side of this point will end up on the other side of the same point, and this kind of trajectory is called an invariant circle. This can also be regarded as spiking at infinitely small frequency, because we start here, produce a spike, and end up in here. So in time it would look something like this. We produce a spike and then are frozen at the stable part of the saddle node. Finally, just after the bifurcation, we have a limit cycle, but near this area our system goes near both of the null lines, as we shall see in the next slide, and because it is close to both null lines, the behavior is very slow here. So this kind of slow valley, and this is manifested in very low frequency spiking. So the interspike intervals are very long here. Now this is illustrated in the following slide here. This is example of a saddle node on invariant circle bifurcations for our model. And if we look at the zoomed up parts here, what we see that at resting state we have a saddle, we have a node, and we have a saddle, and all trajectories wherever we start will be pulled towards the node. And just after the bifurcation, we don't have any equilibrium points here, and all trajectories will just pass this slow small valley here. So this is just before bifurcation, this is just after or at. And this is way after bifurcation. So we increased a lot of the polarizing current in here, and the separation between the two nucleons is more. So this is the V nucleon, and this would be the N nucleon here. And a trajectory will pass here freely, as we will see in the next slide. So here I depicted behavior near the saddle node on invariant circle bifurcation. This is just before the bifurcation, and this graph here shows that if we start at different parts of the phase plane, it doesn't matter where we start from, we will converge to the stable node. So this would be our stable node. And if everything goes right, I can show it in a video. So this is the video. Our purple points are the state of the system, and the fading black lines are the trajectories. So it doesn't matter where we start from, we end up in the stable resting state. Now what happens if we gradually increase the applied current? This will move our V nucleon up, of course, and we will observe the bifurcation. And this is shown in the graph here. So here we increase the applied current. Here, this is our applied current. And at first we are at the resting state, but then this resting state, the stable node, loses stability. No, it doesn't lose stability, of course. It just merges with the saddle. And at first we have quite large interspike intervals, which would be slow spiking or spiking at a low spiking rate. But then as we increase the applied current, the spiking rate becomes higher and higher, or interspike intervals become smaller and smaller. And I'll try to show it in a video too. So this is how it goes. Let's start from the beginning. So at first the system dwells in a resting state, but we are actually pulling the V nucleon up, and you can see that the system slips through the slow valley between the two nucleons, and you can actually see how it slows down in this slow valley, but then it produces the rest of the spike quite fast. But as the separation between the nucleons gets larger and larger, you will see that it takes less and less time for the system to go through this valley. Alright, we see that the spiking rate increases. How lovely. Now let's look at the saddle node bifurcation of invariant circle, which we'll do in the next slide. In here, these are the equivalent graphs. So we start our system at different starting points, shown here, and we either end up in a resting state or we end up in a spiking state. So these trajectories will move to the spiking state, and these trajectories will stay on spiking. And one thing I forgot to mention in the previous slide, that the threshold of the excitable system, or excitability threshold for this kind of a neuron, is actually the separatrice of the stable or of the saddle. And let me show it here. Yeah, so this is it approximately. So the threshold for a neuron is not a fixed value of membrane potential, it's actually a line or a more dimensional manifold. If we start left to this line, we will have a subthreshold response. So we have something like this in time. But if we start from here, or very fast move the system from this state to this state, what we will observe is a typical excitability. We'll have an action potential or a large excursion over the phase plane like this, and we will end up in the resting state. So this would be subthreshold, and that would be suprathreshold. Right. So back to the saddle node of invariant circle, and it is a bistable system. Let me start a video and start it over. So we start from different parts, and you see some of the points converge to the stable equilibrium or resting state, and some trajectories stay on spiking. Right. So how the neuron near saddle node of invariant circle bifurcation switches from resting to spiking if we gradually increase the applied current. In contrast to the previous case, where we observed a gradual increase in spiking rate, we don't see it here. What we see is an abrupt switch from resting to spiking at fixed or almost fixed and at high frequency. So let's see it in a video. Let me open it. Right, so this is the right video. At first we are at the resting state, but we gradually push our V0 line up, and here we go, spiking at a high frequency. And please note, it will be important later, that as we spike, we actually spend quite a substantial amount of time in this corner. So it's kind of a slow corner because it also is near both null lines. Now let's consider the case of the Andronov-Hopf bifurcations. So again, there are two kinds of Andronov-Hopf bifurcations. One is supercritical and the other one is subcritical. In a supercritical Andronov-Hopf bifurcation, what we have, we start with a stable focus, and all trajectories will revolve around it with a smaller and smaller and smaller amplitude. But then the stable focus loses stability, which means that the real value of the eigenvalues changes sign, and from being stable it becomes unstable, and we see that there is a small limit cycle around here, around this unstable focus now. As we increase the applied current, this limit cycle becomes larger and larger, which means larger and larger amplitude spikes. So finally we have full-fledged action potentials, but before that we have kind of subthreshold or partial amplitude spikes. Now in the subcritical Andronov-Hopf bifurcation, our stable focus in here has a limited area of attraction, and this area of attraction of the stable focus is limited by an unstable limit cycle. So all trajectories run away from it, rotating. And then there is a stable limit cycle around it. So this system again is a bistable, or it is a kind of a neuron that at the same sets of parameters can be either resting or spiking at a constant rate. So it just depends on where we start from. If we start from within this unstable limit cycle, we will converge to a resting state. But if we start from outside of the unstable limit cycle, for example from here, or actually from a more hyperpolarized state, it will lead us to stable spiking. But as we increase the applied current, the unstable limit cycle becomes smaller and smaller, and finally it shrinks right to the stable focus, and as it touches the stable focus it loses stability. So finally, just after the bifurcation, there is just an unstable focus and a stable limit cycle. And what we will see here is again a hard transition from resting to spiking, in contrast to supercritical Andronov-Hopf bifurcation. So the case of the supercritical Andronov-Hopf bifurcation is illustrated in this slide. So again, this is just before bifurcation. Just after the bifurcation, you see kind of subthreshold oscillations, and at larger current you have full amplitude action potentials. And it's zoomed up in here, so we have at low current or before bifurcation stable focus, and it's kind of converged to the stable focus point slower and slower, so the damping is actually less and less, and just at the bifurcation there is practically no damping. You have sustained subthreshold oscillations, but after the bifurcation at large current you have a high frequency spiking. So near the supercritical Andronov-Hopf bifurcation, it doesn't matter where you start from, you will converge to a stable equilibrium or a stable resting state. But it depends where you start from. What depends on where you start from is whether you will have an action potential or just a subthreshold oscillatory return to the resting state. So if you start, say, from somewhere here, what you will observe is that you get decaying amplitude subthreshold oscillations in time. But if you start, for example, which is kind of counterintuitively, if you start from a more hyperpolarized state, what you will get is an action potential and then decaying subthreshold oscillations. So in here, the concept of threshold for a neuron, or spiking threshold, is a more complex thing. It's not that you depolarize a neuron and it can result in spiking or an action potential. You can actually hyperpolarize a neuron and get an action potential. Now, what happens if you start from a resting state and gradually increase the applied current, like shown in this figure? So this is our applied current and it's getting more and more, so you shift your V nucline up and up. What you will observe is that first you are at the resting state, but then you get subthreshold oscillations with larger and larger amplitude, but relatively little, if any, change in spiking frequency, but then you get full frequency spikes. So let me illustrate this in two videos. At first we will look at the video with phase trajectories at different starting points. And let me open this. So this is the video. We start from a lot of different points, and all trajectories end up in a resting state. But some of them do actually produce an action potential and some of them don't. Now what happens at the ramp stimulus protocol? So we start from a resting stable focus. So here is our stable focus, but as we gradually increase the current, we get subthreshold oscillations with larger and larger amplitude, but relatively same frequency. And finally, we'll get full-fledged spikes, and you can observe that the rate of the increase in applied current is different in this plot and in this demonstration. So here we go, we have real action potentials. But of course this concept of whether we have a real all or nothing response or not is blurred. So what is a subthreshold response and what is a spike here is not a clearly defined thing. Right, next let's see what happens near subthreshold Andronov-Hopf bifurcation. And again, this system is bistable. So depending on where you start from, so you can start from somewhere here and result in a resting state with dynamics looking something like this, or you can start from here and find a neuron producing spikes at a constant rate at the same set of parameters. Now let me show this in a video. So here we go again. We start from a lot of different starting points, and some of these starting points converge to a resting state and some stay on a sustained spiking regime. Now what happens if we increase our applied current? Right, applied current getting larger and larger, and I can show it in a video too. So basically this is what happens. At first we are at a resting state. Gradually it gets whoops, and we have sustained spiking. Right. Now, what we have done here so far is we analyzed the 4 scenarios of how a neuron can go from resting state to spiking state. So how a neuron can lose its stability. Now let's look at what happens as we go from a spiking state, or where do those limit cycles or stable spiking attractors come from? Again, there are 4 variants. The two of them are actually very simple. It's just the same as going from resting to spiking, but in a reverse direction. These are saddle node and invariant circle and supercritical Andronov-Hopf bifurcations. So if you go one way, like depolarizing the neuron or increasing or applying the depolarizing current, you get from resting to spiking, and if you inject a hyperpolarizing current, you go from spiking to resting in exactly the same manner. Now, two other bifurcations are different. These are called fold limit cycle and a saddle node, saddle Homo-clinic orbit bifurcation. Let's look at them in more detail. But first, let's get through the mirrored bifurcations. The saddle node on invariant circle and supercritical Andronov-Hopf. So in this direction, we are decreasing the stimulation current or injecting the hyperpolarizing current, for example. Again, we start from a spiking regime, But then our V nuclein finally touches our N nuclein. So so this is our N nuclein and this is our V nuclein. So as the two nucleins touch here, as we shift the applied current down, as we shift the V nuclein down, we get the saddle node equilibrium point, and then the two equilibrium points are separated. So one is node and the other one is saddle. What we observe in dynamics is a gradual decrease in the spiking rate. So at first we were spiking at a high rate, but then we get larger and larger in the spike intervals because we get closer and closer to the narrow valley between the two nucleins. And finally, we get this saddle node, which is kind of an infinitely low frequency spiking, and then we just dwell in the resting state. Now in the supercritical Andronov-Hopf bifurcation from the spiking, we have a stable spiking limit cycle which gets smaller and smaller in amplitude until it collapses onto the unstable focus, and the focus is now stable. What it means in dynamics is that at first we have full amplitude spiking, but then it gets smaller and smaller in amplitude, and finally we have a resting state. Let's see it in actual simulation. So we're going from spiking to resting state via saddle node and invariant circle. As we decrease the applied current, we get larger and larger in the spike intervals, and finally the neuron stops firing. If we are going from spiking to resting state by a supercritical Andronov-Hopf bifurcation, what we observe is little if any change in frequency. So the rate of spiking is kind of constant here. Again, here is an applied current and it goes down. But the amplitude of spikes gets smaller. Now, in this system, if we went from resting to spiking via subcritical Andronov-Hopf bifurcation, we were talking about the coexistence of a stable limit cycle and unstable limit cycle and a stable focus. So if we have our decreasing stimulation current here, if we went from a resting state, so this was our stable focus, and then at the bifurcation point, so here the axis is actually the applied current. Then it loses stability and unstable focus. I'll depict here with a dashed line. But at the same time, the system had stable limit cycle. And here what I'm actually depicting is the range of the observed behavior. So you could think of it as the dynamics is jumping or going like this in time, if we look at this in dynamics. So this would be stable spiking. Oops, I didn't mean to delete this one. And here is the unstable limit cycle. Now in the fold limit cycle, we are doing the same but in the reverse. We are doing the same but in the reverse, and what happens is the unstable cycle gets larger and larger in amplitude. So like like here, it gets larger and larger in amplitude, and then the two limit cycles merge, the unstable and the stable one, and as the unstable limit cycle touches the stable limit cycle, they both annihilate each other. And hence the name, the fold limit cycle, because it's kind of analogous to the fold bifurcation when a stable and unstable attractors or equilibrium points merge together. How it looks like in dynamics is that as we decrease the applied current, we flip from spiking to non-spiking regime quite abruptly. So this is a hard transition from spiking to resting. And I should say that there is little change in spiking frequency. Now, if we were losing stability via the saddle node off invariant circle bifurcation, we had a coexisting spiking and resting state. So somewhere here was a stable node, and we had a limit cycle attractor here. But as we decrease the stimulation current, this stable attractor or a stable limit cycle gets closer and closer to the stable manifold of the saddle and to the unstable manifold of the saddle, until it finally is merged in one corner with the saddle. And this is a Homo-clinic orbit because it starts and ends in the same point on the saddle. And finally, as we decrease the stimulation current even more, this limit cycle is unlinked, and now all trajectories, it doesn't matter where we start from, all trajectories will lead us to the stable node. How it looks like in dynamics, as we decrease the applied current, we get a decrease in the spiking rate. So it goes down because this corner becomes closer and closer to the null lines, and as it becomes closer and closer to the null lines, the dynamics becomes slower and slower in this corner, so we observe a slow corner. And I'll show the video once again. This is actually a case shown in here where the dynamics passes through the slow corner and the spiking rate gets down. Now, some further reading can be found in a beautiful Izhikevich book on dynamical systems in neuroscience and in some of the Izhikevich papers. And these are also papers from famous scholars in theoretical neuroscience. And my acknowledgements to great help, motivation, and encouragement from Olga Sosnovtseva from Department of Biomedical Sciences, University of Copenhagen, Denmark. Thank you.